Adam here from Bowhunting Systems. So we're going to continue our video series on momentum and kinetic energy. Today we're going to be taking a look at kinetic energy and what it means for archery. We're going to be attempting to see how it applies to our test that we did in the last video, and to see if we can gain from it any extra explanation and understanding as to perhaps why we got this result from increasing momentum. So if you haven't watched the last video, we did a test where I shot two different arrows, one arrow heavier than the other. They're identical arrows in terms of shape. It's just I upgraded an arrow by adding 150 grains to it, and we attempted to shoot it and measure to see how much performance in the way of penetration it gained us. The results were that the heavier arrow did not out-penetrate the lighter arrow at 25 yards, and in fact it penetrated roughly a centimetre less. So it's not much, but it's measurable, and that was the main takeaway from the materials that we used in terms of the target material, and the way that we performed the test was so that we could get an accurate measurement for exactly how much penetration we could expect from simply increasing an arrow by 150 grains using the momentum equation. So today we're going to go through the same steps that we went through earlier. It'll happen a little bit faster because we already have our measurements that we took for the momentum equation. So we've already got our velocities, we've already got our bow poundage. We can carry a lot of that information over into the new equations that we're going to be using to express kinetic energy. Yeah, so the first up is I'm going to run you guys through what kinetic energy is, and once we've got a fair understanding of what kinetic energy is, we're going to apply it to our test results. Okay, let's get nerdy. Over here I've got a piece of paper that shows the kinetic energy graph, kind of just like what we did with momentum again. I'm just going to run through a couple of the finer points of it, the basics of the equation, and a little bit of history, and how it applies to archery. So as you can see up here in the top left hand corner, we've got some history stuff. That's going to help us to gain an idea of where the idea of kinetic energy came from and why it exists in the first place. So we can see here that it was basically sort of discovered or concreted in the 1800s. We've got two names here, Thomas Young and William Thomson. These are two of the major names. There were quite a few other people involved in the discovery of kinetic energy, with scientists doing loads of different experiments, which were all beneficial in the long run to the understanding of what kinetic energy is all about. But for the sake of just running through history, they're the two major names that I've written in there. And as we can see, this is a newer science. So if we go back to the graph on momentum, you can see that momentum, basically the idea of momentum grew from a very long time ago up until the mid to late 1600s with Isaac Newton's work. And we all know Isaac Newton by name, but fewer people have ever heard of these names, particularly in the archery world. And we don't really know why kinetic energy is a thing, generally speaking, especially in Australia. So why this is important to know is because we need to know why kinetic energy was formed in the first place, right? And I've put here in brackets, it was built on momentum. Now, I had a discussion with a buddy not too long ago where I said this to him, and I got my answer run through artificial intelligence, because, I don't know, it just didn't seem like he understood what I was talking about. When I say it was built on momentum, I actually do mean it in two respects. It was built on momentum in historically. It was historically built on top of the knowledge that we already had in the form of momentum as an add-on, and it also is built on momentum in the way that it includes the same variables. We have mass, we have velocity, and we have an energy output as a result of those two variables. So it uses the same variables, it does something slightly different with it, and so I'm stating that it was built on momentum. And you can run that through AI if you like. I've actually got AI open over here where I've done a little AI search on the question, why was kinetic energy discovered? And over here we can say that it says kinetic energy was discovered primarily to resolve a major scientific debate in the 17th century regarding what physical quantity is truly conserved during motion and collisions. Okay, so we can see there that there was a major scientific debate in the 17th century, which seemed to be surrounding momentum, the ideas of momentum and kinetic energy, and a bunch of people considering that momentum possibly wasn't the best descriptor of it, of motion and collisions. So if we go down to the next part here, it says in the late 1600s, physicists were divided over the measurement of motion. Newton's law, Isaac Newton argued that the quantity of motion was momentum, or mass times velocity. A guy called Leibniz, Gottfried Wilhelm Leibniz, argued that momentum alone could not explain certain physical phenomena, such as a ball bouncing back up. He proposed a living force, or vis viva, defined as mass times velocity squared, which he believed remained constant in a system. So mass times velocity squared, we can see the remnants of that sort of proto-kinetic energy equation here in the kinetic energy equation that we currently have today. So it's mass times velocity squared, right? So it even evolved from what he was proposing. His vis viva equation was mass times velocity squared equals an energy, and he felt like it was a better representation of what happens in some collisions than momentum. Experimental proof. The concept was mathematically and experimentally validated in the 18th century. This is what it says here. William Gravinson's experiment in the early 1700s were that he dropped brass balls into soft clay from different heights, and he found that a ball with twice the speed went 4 times as deep into the clay, proving that the force of motion was proportional to velocity squared, not just velocity. So if he got the balls going faster, they penetrated 4 times as much, right? They 4 times as deep into the clay. If we look at our old equation of momentum, we saw that it was double the velocity equals double the momentum, right? We also saw in our experiment over here that momentum perhaps did not correlate to extra penetration. And what we've got this guy saying is that if you increase the velocity with twice the speed, you got 4 times the amount of penetration, okay? Then you've got another name here, Emily de Chalat. In 1740, she incorporated these experimental results into her work, cementing the mass times velocity squared relationship as a fundamental law of physics. While the concept existed as vis viva, it was formally named and refined later. So this would be the, we're going back to momentum here. This here would be the refining part that they're referring to. So naming. In 1802, Thomas Young was the first to use the term energy in its modern sense to replace vis viva. which was an improvement on momentum. Mathematical formula, the formula half mv squared was refined in the mid-19th century by scientists like Gaspard Gustave and Lord Kelvin, who linked it to the concept of work, force multiplied by distance. Okay, practical necessity. The discovery allowed scientists to understand and improve technologies like fluid dynamics and thermodynamics. So you're coming into the realm of modern science now, where we can see that the applications of kinetic energy are used to a greater extent in the future. So that was just to sort of provide a little bit of background information on perhaps a notion that momentum is, or could be, a dated science compared to kinetic energy, and that kinetic energy is built upon it to better describe some of the collisions and some scientific phenomena that happen in the real world. So if we go over here to our graphical representation of kinetic energy, we can see here that we have, as I said before, we've got our variables. So we've got our mass in kinetic energy is measured in pounds. We've got a v, which is velocity, and that's measured in feet per second. And Ke stands for the amount of kinetic energy yielded, so Ke. And the equation is Ke equals half. So you could write 1 over 2, or I just prefer to use the decimal, so it's 0.5 times mass times velocity squared. Okay. The graph of it better shows this sort of quadratic nature of kinetic energy. As it was said over here in the AI, with artificial intelligence, we've got a link here to William Gravensen's experiments, where he found that a ball with twice the speed went 4 times as deep. We can see a similar nature presented in the equation that we get, or the graph that we get for kinetic energy. So we've got the kinetic energy yielded on the side here, and on the bottom here we have the velocity. And well, this here is the graphical representation of the equation. So to describe how we would use this graph, we'll just go down here and have a look at some of the notes as to how we'll apply this to archery. So Ke is a quadratic function of velocity. This is some of the key differences between velocity, kinetic energy and momentum. If we double velocity, right, so 4 times Ke, so yeah, if we double velocity, we get 4 times the kinetic energy, right? If we triple velocity, we get 9 times the kinetic energy. So the more kinetic energy, the more velocity we feed into the kinetic energy equation, the resulting energy outcome from it goes up exponentially. So it favors velocity. If the more velocity we put into this, the more energy we should get out of it, right? If we go down here, it also says, in archery's inelastic collisions, so if we go back to some of the things that we said in the momentum video, I described in depth what the difference was between inelastic collisions and closed collisions. In archery's inelastic collisions, so we have inelastic collisions in archery where objects don't bounce off one another. They deform, they deflect, they bend and absorb. They're not just rebounding off one another. So in archery's inelastic collisions, Ke is never conserved, but is transformed, right? So the description of momentum was that momentum was always conserved. So there's a key difference here in the idea that kinetic energy is said to be never conserved, but is transformed, right? So another point is that kinetic energy is scalar. So it can never be negative like momentum, only positive, right? So we can have, if we go back to our old explanation of momentum, momentum can have positive and negative values because it's linear. So you can have positive momentum of an arrow moving towards a target, but you can also have negative momentum from an animal perhaps moving in towards the line of fire of the arrow. Whereas kinetic energy, whoa, that might actually help us if I've got both side by side here. So kinetic energy isn't described in that manner. It's scalar. So that means it can never be, you can never have minus kinetic energy, if that makes sense. So kinetic energy simply relates to the amount of energy that the moving arrow, or the potential it has to do work. So K is a non-directional energy as well. This is another thing to consider as a difference to momentum. So momentum is a directional force. So whatever the direction of momentum is, we can expect the results to be going in that direction. But with kinetic energy, it's non-directional. So you can lose kinetic energy 360 degrees from the object that's in motion, right? And quite often you do, because it deals with drag, it deals with heat loss, it deals with the deformation of the target, which happens in all directions once the impact is made. It separates the target this way, this way, this way, and it changes and varies. It describes the damage that is caused within the target as a direct link to the amount of kinetic energy stored in the arrow. So yeah, it says here it can be lost in many forms and directions: drag, heat, deformation of the target. See thermodynamics. So thermodynamics relates to those things, and that's a whole nother field of physics that we're not really going to get into here, although we can know and understand that by over here we can see the links presented in our study notes that kinetic energy is intrinsically linked to the study of the sciences of thermodynamics and fluid dynamics, and we can see that there's an interrelationship here between kinetic energy and those sciences. So again, we've already stated that kinetic energy deals with the same variables as momentum. So it's not like if you play with the variables of one, you won't be affecting the other. It's not like, okay, we're going to do kinetic energy stuff now and we can forget about momentum having anything to do with our stuff here. If we're only dealing with increasing kinetic energy, then momentum gets left in the dust and nothing happens to it. That's not the case at all. Because we're dealing with the same variables, mass and velocity, right? Because we're dealing with the same variables, it means that if we adjust our equations to give us better kinetic energy, we will be by default increasing momentum, right? So if you want to increase the variables to get better performance out of your gear using the kinetic energy graph or the kinetic energy equation, you're increasing either one of those variables, you would be increasing your momentum as well. Does that make sense? So if you're changing mass and velocity here to get a kinetic energy result, you would also be getting a different momentum result over here as well. It's just that the modern science, the use of kinetic energy, better describes the effects downrange of our archery equipment than the science of momentum did. And it's not like we're not including the science of momentum anymore, because we're using the same, like we can actually definitely see the same mathematic principle, mass times velocity, over here. That is in itself, if we take away the squared value, it's still mass times velocity. It's mass times velocity squared, right? So it's still a momentum equation. It's just been beefed up to explain other things that we get from the collisions, and in specific archery, it explains the collisions that we get and the effects of our archery gear differently and better, because it incorporates all of these other things that affect the arrow during its flight and during the collision. All right, so I feel like we've gone over kinetic energy enough now to know that its origins lie in it being an updated measure to describe things in physics to momentum. You can still use momentum, okay, but you're gonna see shit like this happening, and you won't really know how to explain it until you start using the kinetic energy formula, right? So that's the next part of our video anyway, is to introduce you guys to the kinetic energy calculator. So here we have our momentum results, and we're going to start a new sheet by carrying over some of the results that we got from our momentum experiment. So we've just simply carried over the feet per second because that doesn't change. None of this stuff changes for the use of the kinetic energy equation. The mass, however, does. For this, I mean, it's also nicer to use, to be honest with you. We don't need to convert these values into slugs for this, so we can keep just our standard grain weights. All we need is the velocity output of our bow applied to the arrow. So you still need your bow scale, you still need your arrow scales, and you still need your arrow speed calculator. So if I just go back to here, again, I've included the arrow speed calculator in at the footnotes of my last video on momentum, and I'll include them on this one as well, just so that you guys have quick access to it. The only thing that we do differently for this is change the calculator. So if we want to work out the kinetic energy, we got to go over here and use a kinetic energy calculator. Okay, so if I go over here, kinetic energy calculator. Okay, if I scroll down here, it asks us for our arrow weight in grains. So I just go ahead and plug in. So we'll do the 400 grain calculation first. So 400. And arrow velocity in feet per second. So 297. 297. Okay, and it does give us our result pretty quick there, so 78.37. So if I go over here, 78.37. Yep, and that's in foot-pounds per second. Yeah, so it says over here, in foot-pounds. So yeah, we'll just leave it like that, 78.37. And we'll go ahead and we'll do the same calculation for the heavier arrow, 550 grains, and the velocity is 247. 247. Okay, 74.53. So 74.53. So we can see there that our kinetic energy values are different, and they're favoring the lighter arrow now, which is interesting because our results were that well, if we have a look at our previous results first, our momentum results showed us that the slightly heavier arrow, the 150 grain heavier arrow, gave us, what's that, 3, 4, 5, 6, 7, 8, 9. So 0.06 of an increase in momentum. So it wasn't very much comparatively more momentum than the lighter arrow, but the heavier arrow under the momentum equation gave us a slightly better value in momentum, but that didn't correlate with better penetration. So if we have a look at kinetic energy, we can see that the kinetic energy of the lighter arrow is slightly greater than that of the heavier arrow. So the kinetic energy is 78.37 foot-pounds, and the kinetic energy of the heavier arrow is 74.53 foot-pounds. And if we go down to our penetration, we can see that the increase in kinetic energy achieved by the lighter arrow, it's not a light arrow, it's just lighter than the other one, right? So, but the lighter arrow gave us a kinetic energy reading that correlates to the small improvement that we can see in penetration here. So it improves slightly better in terms of penetration than the heavier arrow does, and it also has slightly more kinetic energy than the heavier arrow does. So essentially what we've found here in our findings for kinetic energy is that a penetration value, we can expect a greater penetration value of an arrow if its kinetic energy is higher. So that was I'm just showing you guys how to work out kinetic energy on a calculator. We've applied the science of kinetic energy to our two arrows and their performances, and we now have an updated value in terms of kinetic energy that we're going to go over and discuss. It's bloody hot out here today. I hope you guys got something out of that that little trip down the road of kinetic energy calculations. The key takeaway from that for me is that kinetic energy is a lot easier to use in terms of arriving at a result. I know we didn't have to do all of the work that we did to obtain all of our velocity values, and you'd still have to do that even if you were just going to use the kinetic energy calculator. You would still have to go and measure your bow poundage, work out your arrow speeds and all that sort of thing. But the real benefit of that particular calculator is that you don't have to convert your arrow grains to anything. You can just plug the measure your arrow weight and pop it straight into that calculator. So what we're going to talk about now is we've already sort of briefly gone over the results. We can see that we know that the lighter arrow, the 400 grain arrow, I should stop calling it the lighter arrow because it's misleading. I don't want people thinking that they can just game the system by just choosing the lightest arrow that they can and that it'll yield more kinetic energy, because I can tell you it doesn't. I have been down that road, and we get into the ugly side of trying to game these sciences to our advantage, and that is that it's the same principle that we discussed with momentum. It serves us better to include an increase in mass as well as velocity, even with kinetic energy. Like, we can't just continuously increase velocity and decrease mass like it's not important to try and get more speed, because it just doesn't work that way. We're going to go into detail about why not a little bit later, and I have done that in the past, and it is kind of funny, but it's a bit of a funny story. But we'll go down that road in a bit. First of all, I wanted to talk about the results and how we can see those results reflected in our testing. So first thing to consider is that the measurement that we are taking is of the kinetic energy, or if we go back to our momentum equations, we're measuring the momentum as it leaves the bow. If we're talking about kinetic energy here, because we're not using a chronograph downrange out the target face, we're measuring it as it leaves the bow. And the reason I'm doing it like this is, one, because I don't have a chronograph, and two, I don't need one. So my results are basically what I'm trying to change and what I'm adjusting to get better performance out of my arrows is the equations that give me the kinetic energy or the momentum that I'm receiving as my arrow leaves the bow. As far as I'm concerned, the effects that both arrows have been put under as they leave the bow and as they're shot from the bow, the potential energy and the natural environment has affected both arrows in terms of the quantity of its effect at an equal proportion. So basically, yeah, if I did have a chronograph, I would put one out there, and we could get even more detailed results. But again, I'm just wanting this to be a user-friendly experience, like you don't have to go and buy a chronograph to be able to do this sort of thing and express these sorts of results. You can just go and buy, your run-of-the-mill bow scales and arrow scales and some cheap equipment, and you can achieve these sorts of scientific outcomes without the necessity to go down the road of buying a chronograph. Anyway, we can see that a slightly increased value in kinetic energy that is present in the 400 grain arrow is represented by its slightly increased penetration here, and a slightly decreased value in the amount of kinetic energy contained in the heavier arrow has yielded it a slightly lower amount of penetration. So the amount of work this lower arrow was able to perform was less than the lighter arrow. The lighter arrow had more potential to do work, and the heavier arrow had less potential to do work, as described by the value we got when we measured its kinetic energy. So overall, we're talking about a difference in penetration here that is like 1 centimeter. So the value of extra penetration by adding weight, even 150 grains, in my opinion, which is influenced by the results of the testing that I do, is that it's not worth the sacrifice in performance, in trajectory. It's not worth the sacrifice in trajectory for me to go out of my way to buy heavier arrows, and for me to buy arrows that are 550 grains, it is more expensive. And I just don't see the benefit of it. If I'm only going to be negatively impacting the performance of my bow, like perhaps at a lower poundage, maybe that would be different, but I just see the overall science of kinetic energy as a better science to go by, a better equation to go by for predicting the performance of my arrows. So the higher the kinetic energy is in my understanding of things, the better performance I'm going to get out of my arrows. But there's more to it than just penetration when it comes to arrow performance as a whole. If we're talking about penetrative performance, then yeah, increasing the amount of kinetic energy is going to give me higher penetrating power. But what does increasing the mass do for my shootability of the bow, or the trajectory performance? And that seems to be where the biggest variabilities in results come from, if you ask me, is that the decrease in speed in relation to the arrow mass seems to have a greater effect negatively on my the flat shooting nature of my bow. Like, it affects it more so than it does the penetrating power of the arrow. That's pretty much it. In the next video, I'm going to be talking with you guys more about perhaps why 35 yards might be the limitation for me due to some of the equipment that I choose in the realm of broadheads, and why I've imposed that limitation on myself, and why perhaps another hunter may not have to. This 35 yard limitation is something that only works really for me and my setup. Everyone's setup is different, but the main takeaway from this video, I'm hoping everybody understands that kinetic energy has been built on top of momentum, the science of momentum, and it better represents what we're seeing in the collisions, the inelastic collisions of archery. And it correlates better to the penetration that we're also seeing on our targets, which are at a uniform density, as I discussed earlier when I was talking about the why our target is made out, why this target's made like this. It's uniform, which means that we're going to get a measurable amount of penetration, so that we can compare without wondering whether or not one part of the target was denser than the other, etc., etc. So kinetic energy, as far as I've understood it to be, is a more effective mathematics tool in working out the performance of my arrows. I'm going to include all the calculators, so the kinetic energy calculators, and I'll throw the arrow speed one in there as well in the footnotes of the video, along with any equipment that that I use. I might include my actual bow, and so that you guys can look it up and have a look and just check, make sure that I'm actually quoting the correct IBO readings out of it. In the next video, like I said, I'm going to talk more about like the limitations of the limitations of the equipment that I'm using in regard to broadheads, and specifically how we can apply kinetic energy, the kinetic energy output of our bow and arrow system to hunting specific game types, as well as to like how much kinetic energy do I need to hunt a deer, or how much kinetic energy output do I need to hunt a pig. I'm going to cover all of those things in the next video as well. I hope you guys have enjoyed this. I hope you haven't been overwhelmed with any of it. Please use those calculators when you guys are working out what equipment you want to use. Even if you're going to just use the momentum calculator, at least use the momentum calculator to see whether or not you're actually going to get better performance out of your equipment, or the amount of performance increase in relation to how much money you're prepared to spend on stuff. Alright, I'll see you guys in the next video.